Our last system is base 16 or hexadecimal. And hexadecimal is also good to know. Now we have 16 digits. And so the way it counts is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But because we have 16 digits, our next number will be A. A represents our ordinary number 10, 11, 12, 13, 14, 15. And so A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So the common thing to do with base 16 is to substitute the first letters of the alphabet up through our ordinary number 15. So that means that in computer code you could see, or printouts, you could see numbers like A93B, for example. A93B is a 16-bit number, okay? Because each place value in hexadecimal carries 4 digits in binary. 4 digits in binary can take you up to 15. And so 4 of these place values would require 4 times 4 times 4 times 4, I mean 4 plus 4 plus 4 plus 4, 16 binary numbers to represent. Alright, so our job is to go back and forth learning how this works. And we can also do the conversions. And I suppose we should start with converting from hexadecimal numbers to decimal numbers. So I'll do a couple of those, but if you've gotten good at the binary and octal conversions, this isn't a whole lot different. So I'll do a couple of these. So the number I made up a moment ago was A93B. That's a hexadecimal number. And I think for consistency I'll put a little 16 there. Although if you see letters appearing, then it's going to be hexadecimal. Alright, so my chart, now the numbers get kind of large because, you know, the first place is always the ones. The second place will be the base number, 16. Now 16 to the second power is 256, so the third value is literally 16 squared, or 256. And the fourth decimal place is 16 to the third. 16 to the third I think is 4096. Let me double check. 16 raised to the third, 4096. Okay, so that's going to be a decent sized number. That means A93B in hexadecimal is going to be, wait a minute, A was 10, here's 9, 3 of these, and B is what? B is 11. So if you need it, have that chart by your side. After 9 comes our regular 10 is letter A. 11 becomes B. 12 becomes C, and so forth. So this will be 10, 9, 3, 11. So this will end up being 10 times 4096. 9 times 256 is 2304. 3 times 16 is 48. 11 times 1. So let's see, this is 12, 13, 7, 8, 12, 10, 13, 3, 4. So this is equal to 43,323. So I'm going to double check that. 4096, 0, plus 9 times 256, plus 3 times 16, plus 11 is 43,323. Okay. So there we go. That's converting a hexadecimal number over. Let's do one more. Here's one more example of a hexadecimal number that will convert to base 10. And I wanted to take advantage of the letters, and so it's mostly letters. 7FCA, base 16. So we have a 7. F is what? So run down through the list. 10 starts at A. So A, B, C, D, E, F. 10, 11, 12, 13, 14, 15. F is 15. C, you can do the same thing. C is equal to 12, or 12, and then A is equal to 10. So this would be 7 times 4096 plus 15 times 256 plus 12 times 16 plus 10. And I'm just going to run that through a calculator. So 7 times 4096 plus 15 times 256 plus 12 times 16 plus 10. I get 32,714. Okay, base 10. So there it is. All right, now we can discuss converting base 10 numbers back to base 16 numbers. It's very similar to how you would work with octal or even with binary. And let's do a short one. For example, if your number is 97 in hexadecimal notation, oops, I'm sorry, it's not what I meant. Suppose it's 97 in ordinary, base 10, and want to convert to hexadecimal. Divide 16 into 97. Well, it goes 6 times. 6 times 16 happens to be 96. So this would be 6, and then the remainder is 1. So in hexadecimal, or base 16, 97 would be 61, base 16. And so anyway, that's kind of the idea. I think if you needed to, just follow the same similar steps as we did for octal. I think more commonly, you would see hexadecimal used to represent long binary strings of numbers, much like octal is used for that purpose. And so let me run through a couple examples here. I wrote a 6-digit hexadecimal number up here, F32A19, base 16. And one nice thing is that it's a very somewhat concise way of representing a much longer binary number. And so how does that work? Well, in hexadecimal, each decimal place represents 4 digits in binary. And so now this requires that you learn your conversion from binary to hexadecimal and back, or to decimal systems. Remember that F is the number 15, ordinary 15, and in base 2, 15 is 1111. So if you need it, write up a little chart, the numbers 0 through 16 in binary, base 2, and then you could also list decimals, octal, hexadecimal. So you could have a chart where you can immediately do conversions. So F, number 15, is 111 in binary. 3 is 11, so I'll put in the 2 leading zeros because each one represents 4 decimal places. I mean 4 bits of information. So F32A19 is 1111 for F, for 15, 011 for 3, 010, 0010 for 2. A is 10. 10 in binary is 1010. 8 plus 2 is 10. 1 is 0001, and 9 is 1001. Okay, so got all that down? So if you have a chart next to you, you can write that down. I've seen these when I used to do programming myself. Sometimes I could get some kind of a printout of code in hexadecimal, And the way it stored the graphics, the pixels, were in these kind of numbers. These are 24-bit numbers. And so I think it's common for a computer screen to have 24-bit color. 24-bit color means, as I explained earlier, that the three primary colors, red, green, and blue, are represented this way in order. So 24 binary digits is 24 bits. And when you think of it, these are bytes. A byte is 8 bits, okay? So it's 3 bytes, each byte, 1 byte for each color. And so each place value in hexadecimal is 4 places in binary, 2 digits in hexadecimal is a byte, or 8 bits. And so F3 represents how much the red is turned on in that pixel. So your screen, your computer sends a signal to the screen, whatever generates colors on the screen. It lights up the red part of that pixel to this degree of intensity. Now I don't know what that number is, but we could calculate it pretty quick, because F3 would be 3 plus 15 times 16. So that would be 243. For red. For green, 2A would be 2 times 16 plus A is 10, plus 10. So that would be 42. And blue would be 19, so that would be 1 times 16 plus 9 is 25. And so this, as a color, and I have no idea what this looks like, but it's more green than anything, so it's some off shade of red. I'm sorry, it's more red than anything, it's kind of off shade of red. So the strength on red would be 243 with a little bit of green and a little bit less blue thrown in. And so it lights up a particular shade on there. So anyway, this number, I guess I wanted to illustrate is this number can be thought of in hexadecimal as a 3-byte number. Each 2 digits represents a byte, or 8 bits. And if we're talking colors, then here's red, green, blue. Okay, I think that's how it works. So if I'm wrong, your computer faculty are going to have to correct me on that. But anyway, that's a way of looking at this. All right, so let's try 1 or 2 more of these. And let me erase the board. Here's another 24-bit number. And I put a leading 0 in front, just so there was 24 place values. So let's look at this. What would it be in octal? First I'll do the octal base 8 representation. And so for octal we divide these into 3s. And so this is going to be 2. 4 plus 1 is 5. 4. 2. 4. 2. 7. 5. Base 8. So that'd be 2, 5, 4, 2, 4, 2, 7, 5, base 8. Okay, that's the base 8 representation, if you like that. Let's do the base 16 representation. And so let me see, I'm going to have to erase these a little in between. So for base 16, or hexadecimal, we're going to divide these up into 4s instead of 3s. Okay, so there, 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 and there. And I think I accidentally erased a 1 over here. I hope that was a 1. Alright, so hexadecimal, let's take it 4 at a time. Let's see. Now, I'm still converting base 2 to base 10. So this is 1 plus 4 is 5. 4 plus 2 is 6. 2. This is 8. This is 8 plus 2 plus 1 is 11. 11 is B. And 8 plus 4 plus 1 is 13. 13 is D. So this number would be 5628B D, base 16. Okay, so there it is. And so a 24-bit number represented somewhat more concisely. And I think as you'd probably much rather face a smaller page of hexadecimal numbers than a very large page of binary numbers. Binary numbers is just going to be gazillions of zeros and ones. All right. However, you really cut the length of a binary number by 4. Okay, when you go to hexadecimal. So it takes 24 bits to represent this number, or digits to represent this binary number. And 24 divided by 4 is 6. It only takes 6 digits to represent that in hexadecimal. And alright, so now if you find it easier to convert, if you need to convert this to base 10, you can decide if you want to convert it using binary, if you want to go to octal and convert it, or if you want to use hexadecimal and convert it. Okay, your choice. But anyway, you should know how to go from one to the other, back and forth. So let's do one more. Here are 4 bytes of information, and let me challenge you to write this in both binary and octal. All right, so I'm going to do a binary first, and so A is 10. 10 will be 0, 1, 1, 0, 1, 0. 1, 0, 1, 0, that's 10. And then 0 will be 4 zeros. 3 is 0, 0, 1, 1. 7 is 0, 1, 1, 1. E is what? 14? 14 is 8 plus 4 plus 2. Okay, so it's 1, 1, 1, 0. 8 is 1, 0, 0, 0. F is 15. 15 is all ones. And then 2 is 0, 0, 1, 0. Base 2. So it's kind of hard to write on the board. I should have been writing smaller. So let's double check this. Okay. A is ordinary 10. That's 8 plus 2 is 10. 0 is just 4 zeros. 3 is 2 plus 1. 7 is 4 plus 2 plus 1. E is number 14. That's 8 plus 4 plus 2 plus 0. 8 is 8, 0, 0, 0. F is 15, 1, 1, 1, 1. And 2 is 0, 0, 1, 0. All right, so there it is. And that's what it is in binary form. Now, if we want to go to octal form, let's see, I got to think about that a little differently. And I need to think of it in pieces of 3, and I'm looking for a different color pen. I can't seem to find one, so I'm going to, anyway, while I'm fiddling with this, why don't you try to convert that to octal. Alright, we'll try this in octal. Okay, I managed to erase all the marks in between. Now in octal, as you remember, we go with every 3 places instead. So, starting here, and those are base 2, so I convert them to base 8 numbers. That's 2, 4, 0, 1, 5, 7, 6, 4, 3, 6, and 2, base 8. So this would be 2, 4, 0, 1, 5, 7, 6, 4, 3, 6, 2, base 8. Wow, converting from, if you wanted to convert directly from base 16 to base 8, Wow, I'd have to think about that one. Off the top of my head, I don't know a quick and easy way to go from this system to that system. So probably the easiest way is to go to binary, then come back to here. I don't know if that would be something you would ever need to do, convert from base 16 to base 8, but that's one way you could do it. So anyway, I hope this has been useful to you, and give you some ideas of how to convert between the various systems, the various base systems. And good luck.